press the bell icon on the YouTube app and never miss another update.
Yeah, hello dear students. Yeah, let me enter into the part 13 from systems of particles and rotational motion. So in last part we covered only a torque. Okay, up to the last part 11 I covered center of mass and some beautiful concepts also covered. Okay, no doubt all concepts will help a lot for all type of entrances. JEE, NEET and every entrances, KSET, including KSET. Anyhow, in the last one, we know the meaning of torque. We know the torque nothing but it is the cross product of position vector and force. Otherwise, force into perpendicular distance. And I solved some problems and we know the direction of the torque. Now let me continue. Next topic, angular momentum. So write down angular momentum. Angular momentum. So in last laws of motion chapter we learned linear momentum. Here the same term we can use it as angular momentum, that can be represented as L bar, capital L. Let us see how to get this angular momentum. Okay. So this is also means this angular momentum also a vector and the directions are similar to like a torque. Okay. Direction of angular momentum also similar to like a torque. It is also one cross product. Let us see how to get this cross product. Let us suppose if a particle moving along a straight line, let us suppose straight line in any plane, in a plane, let us suppose the plane is xy. See, this is something xy plane, x axis, y axis. Now the particle whose mass is m, which is moving with a speed v, and this is the position vector. You know these things. Now the target is to find out angular momentum about this point O. Okay, earlier we calculated in the last topic we done torque about O. Now I am going to calculate angular momentum about the point O. Here once the particle is moving in xy plane, this particle have linear momentum. Mass and velocity nothing but what? Product of mass and velocity, call it as linear momentum. Okay, and here this angular momentum about O we can define as vector product of position vector and linear momentum. Linear momentum is a vector. Okay, it is also like a cross product about this. See, this is the momentum and resolve this one into some components. See, if it is theta r cos theta and see the shortest distance, this is r sin theta. R sin theta is the shortest distance and these two will equivalent to angular momentum. Okay. So here the momentum, this is the linear momentum and perpendicular distance. Earlier we know force into perpendicular distance, call it as a torque. Here linear momentum into perpendicular distance. What is the perpendicular distance? R sin theta. What is the linear momentum? mv. mv into r sin theta. mvr sin theta. Okay, mv nothing but p. p into r sin theta. pr sin theta. Nothing but r cross f. Nothing but like a cross b. So angular momentum about point O we can written as angular momentum about point O we can written as m into like a cross product r bar cross v bar. So angular momentum nothing but m into r bar cross v bar. We can write L bar which is equivalent to r bar cross m into v bar. So L naught we can write r bar cross p bar. See, this is the angular momentum equation. R bar cross P bar nothing but RP sin theta. Okay. So angular momentum about O we can define as cross product of position vector and linear momentum. So let me recall the definition. Let me repeat. Angular momentum of a particle about O, angular momentum of a particle about O is defined as the vector product of position vector and linear momentum. It is the vector product of position vector and linear momentum. So this is also like if this is A vector, this is B vector, this is equivalent to C. Directions are similar to torque. So angular momentum about O is defined as vector product of position vector and linear momentum. So this is the angular momentum equation about this point. We can write L about O, we can write RP sin theta. If theta 0, angular momentum 0, theta 180, angular momentum 0, theta 90, angular momentum maximum. Okay, so angular momentum nothing but momentum into perpendicular distance. Okay, so this is the case when particle moving along a straight line. First suppose, okay, so this is the main equation. Okay, if this particle, if any particle is rotating about a fixed axis, let us suppose I am going to find the particle is rotating about a fixed axis like this. This is the particle whose mass is m, rotating about a fixed axis. Let us suppose this is something z axis into the board or out of the board, and r is the perpendicular distance. Yeah. Okay. Now let me write angular momentum of this one about O. About O. If a particle is rotating about a fixed axis, that fixed axis we can call it as what? Axis of rotation. Now let us write the angular momentum of the particle about this O. Okay. So anyhow angular momentum is mvr. If theta is equal to 190, see, if I write theta 90 sin 91 L naught, which is equivalent to RP, P nothing but MV, so let us write MVR. Okay, this is L about O. Same way, now the particle here is moving along a straight line. If it is rotating about this point O, now tell me the angular momentum. If it is rotating about this point O, then L about O is momentum and perpendicular distance. So if we draw a tangent, that tangent will give the speed of the particle, velocity of the particle. See, this is the axis. Now the particle is revolving like this. Now somewhere the particle is here. If you draw the tangent, that tangent will give, tangent means straight line. If you draw the tangent, that tangent will give the motion of the particle at that point. Now tangent is into the board, so MV, and this is R. MV, R. See how these two perpendicular to each other. Then this product MV and R is nothing but angular momentum about this O. Angular momentum about O, MVR. In the same manner, if they ask to find the angular momentum of the same particle, now the particle is rotating like this, about this point, O is outside. So tell me the angular momentum of the particle about this point, about O, MVR, about this O, MVR. Now the O is outside. Okay, this is the axis of rotation. O is here, particle is rotating like this. With respect to this point, decide the angular momentum. Now the particle is moving like this. See, this is the axis of rotation. Now the particle is rotating like this. Imagine correctly. Okay. Now if you draw a tangent, this tangent will use what? Speed. Okay, on board the diagram is looks like this. Imagine in a 3D manner. So what is this? Perpendicular distance. Okay, perpendicular distance. And this is perpendicular distance, and just you see if I take any particle here, this is V, okay, out of the board. So the diagram is looks like this, but that is complete 3D picture. So this is this wire, axis of rotation, particle is rotating like this. If you draw a tangent, this is the tangent, okay, this is the tangent, and from O you draw a line, from O you draw a line to that tangent. Imagine correctly, from that point O you draw a line to the tangent. No doubt if I draw a line to the tangent, and no doubt this is R, and the angle between these two, okay, diagram is not clear, but angle between these two definitely 90 degrees. Okay, no doubt angle between this MV and R definitely 90 degrees. Imagine in a 3D way, draw correctly. So angle between them is 90 degrees. So with respect to this point, again the answer is same. Now angular momentum is mvr. Angular momentum is mvr. We can write v as a r omega. Why? Because we know the relation between linear velocity and angular velocity. V is equal to r omega. You will get one more equation. Okay. So let me show one more equation of angular momentum. So this is the basic equation. Angular momentum when a particle moving along a straight line. If possible, you try to remember these two. Now let me get angular momentum of a rigid body. So angular momentum also a vector quantity like a torque. So try to remember the next one, angular momentum of a rigid body, system of particles, rigid body. Yeah. So anyhow, so far we know one is torque, other one is angular momentum. Okay, almost both are same, directions also same. Now let me find angular momentum of a rigid body. Next I am going to continue the relation between torque and angular momentum, both. Okay, angular momentum of a rigid body. Let us suppose this is the rigid body whose mass is m, and this is rotating about one fixed line. Okay, about let us suppose the rigid body rotating like this with an angular velocity omega. Rigid body is rotating with an angular velocity omega, and I am going to find angular momentum of this rigid body whose mass is m. To find the angular momentum, let us take a small part. Again started integration. When I use small part means then you can think for again I am going for integration. Okay, don't worry about the integration. I am telling you number of times, first year students especially. So here at a distance of something x or whatever, at a distance of x, let me take a small particle whose mass is m. Once this is rotating about this axis, this entire body also rotates with same angular velocity, and this particle also rotating like this with same angular velocity. And if you draw any tangent, no doubt that the tangent will give motion of that particle. Okay, of course it is rotating like this with angular velocity omega. If you draw a tangent at that point, that tangent gives the what? That tangent gives motion of that small particle whose mass is dm. Okay, and this dm and v, nothing but what? Momentum, small momentum of the small particle. whose mass is dm. And this v, see, I am going to find angular momentum of the small particle. Angular momentum of the small particle, let me write dl naught. For small means generally we use dl, dx, dy, all are the small words, okay, small particles. dl means angular momentum of small mass, which is equals to, we know angular momentum is mvr. M nothing but dm, v, r nothing but x, r nothing but x, and d l naught dm. What is v? V is equals to r omega. Why? Because the particle is rotating. If any particle is rotating about a fixed axis, then we know v is equals to r omega. Recall derivations from vectors before the centrifugal force derivation. Here v is equals to r omega, r nothing but x, x omega, and this x. So d l naught is equals to d, okay, let me write x square omega into dm. Just apply the integration. Apply integration. Then integration of d l naught. This is L naught. Integration of x square omega dm. dl naught is L naught. X square omega constant. Integration of dm is m. So we will get L naught is m x square omega. I am getting L naught is m x square omega. And see this m x square, nothing but, what is this m? M is the mass of this rigid body, total mass of the rigid body. X is the distance. Okay, x is the distance from where? From where? From axis of rotation. And see, we are getting one product of mass of the rigid body and square of the distance from axis of rotation. See, I am getting one new equation here. Observe this one. What is this mx square? Mx square is the product of mass of the rigid body and square of the distance from axis of rotation. This quantity, call it as capital I and omega as it is, where I, which is equivalent to mx square, this is called as one more new quantity, that is moment of inertia. Yeah, one more new quantity is coming now. What is I? Moment of inertia. Don't worry, I am going to continue this moment of inertia in the next classes. Okay, so right now you keep in mind I is nothing but moment of inertia. So finally we got L is equals to I omega. Keep in mind L is equals to I omega. What is I? Moment of inertia. You know inertia in laws of motion. What is inertia in laws of motion? It is the inability, it is the opposition offered by itself, by state of rest or state of motion. Okay, state of rest or maybe with uniform motion. Inertia nothing but opposition offered by itself. Here the moment of inertia. Okay, I will continue moment of inertia in the next sessions. Okay, so what is I? Moment of inertia. Now finally I got angular momentum of a rigid body when it rotates about a fixed axis. L is equals to I omega. Keep the formula in mind, that is useful for solving some easy level of problems. L is equals to I omega. Take it. You are completed? Now let me continue some more basic derivations useful for your board level. A relation between torque and angular momentum. Yeah. So this is important for your board level exams. Let us get the relation between torque and angular momentum. Anyhow, we know torque is nothing but what? R cross F. Okay. Now let us get. We know angular momentum is, what is angular momentum? R cross P. R cross P. Let me derive in a mathematical way. So L bar we can write it as R bar cross P, nothing but M V bar. M is a constant. Okay, M is a constant. Now let us apply derivative for this. Apply derivative with respect to time. Then this can be written as d L bar by dt. D by dt of R bar cross M V bar. I am applying simple differentiation. Okay. So comparing to integration, this is nothing for you especially. Okay. So dl by dt, and multiply this d by dt for this term. dl bar by dt, which is equivalent to 2. Multiply d by dt for first term. So let me multiply dr bar by dt cross mv bar, plus multiply this d by dt for the next term, r bar cross dmv bar by dt. Okay, just I multiply for first term cross mv as it is, multiply this d by dt for next term, keep this as a constant as it is, r bar cross. Okay, so d L bar by dt, dr by dt nothing but v bar. Okay, dr by dt nothing but v bar plus r bar cross, you write m outside, m into dv bar by dt. Mass is a constant. Mass is a constant. So dl bar by dt, which is equivalent to 2, you write m outside. Okay, I am using plenty of steps, v bar cross v bar, plus here r bar cross m into, what is this? A bar. dv by dt is a bar. Recall the cross product rules. I cross I 0, j cross j 0, v cross v. Cross product of two same vectors always 0 because angle is 0. So dl bar by dt, this is m into 0 plus r bar. What is m into a? F. What is this r cross f? What is that r cross f? R cross f nothing but torque tau. So dl bar by dt, which is equivalent to tau bar, because r cross f is tau, m into 0 0. Now dl bar by dt is tau. So torque also defined as the rate of change of angular momentum. Torque also defined as rate of change of angular momentum of a rigid body. So I got relation between torque and angular momentum. Simple differentiation. Okay, we will get the same relation for a systems of particles. Let us use some summation, you will get some systems of particles. So that also I will write in a matter of 2 steps. We take this first, useful for board exams. Okay. Completed? See, again I started very slowly, torque, angular momentum, again next, again you expect some integration problems from my side, okay? Okay, based on situation I will cover. If you are struggling with integration means I will avoid. I will use direct formula. Completed? Now let us get one more. The same, just I am following some NCERT, few steps only. A relation between torque and angular momentum for system of particle. For system of particles. Systems of particle or system of particles. The same step, see, for systems of particles nothing but what? Rigid body. Okay, rigid body. Rigid body means it consists of number of particles. Okay, let us consider a rigid body. Consider a rigid body whose mass is m. Consider a rigid body whose mass is m. It consists of number of particles whose masses are m1, m2, m3, m4, so on, mn. Okay, consider a rigid body whose mass is m, then it consists of a number of particles of masses m1, m2, m3, so on, mn. Once the rigid body is set into rotation about a fixed axis, then that rigid body will have angular momentum. Rigid body have angular momentum. So, if m1 is rotate, that m1 particle have angular momentum. m2 rotate, m2 particle have angular momentum. m3, m4, m5. So let us consider, okay, consider n particles, okay, consider L1, L2, L3, so on, Ln are the angular momentums of n particles. Consider L1 bar, L2 bar, L3 bar, so on, Ln bar are the angular momentums of n particles. N particles whose mass is m1, m2, m3, so on, whose velocity is v1, v2, okay, whose distance is r1, r2, like that. So, L1, L2. Now, the total momentum, total angular momentum, we can write this total angular momentum. We can write L total, we can write summation of Li from I is equals to 1 to n. Li from I is equals to 1 to n. And if you apply differentiation with respect to time, you will get dl by dt. You will get dl by dt. And this can be written as, see, dl by dt, okay. This we can write L particles, mvr. So we can write as m particles. This one. Yeah, sorry for the delay. See, so what I consider L1, L2, L3 are n particles whose angular momentums of n particles. Now apply the differentiation. On both sides, dl by dt. So this can be written as d by dt of, see, summation of I is equals to 1 to n li, and see, again something is missing here, just a minute, here again there is a difference. So apply differentiation here again. Okay. So dl by dt, suppose it is a vector. This, let me write dli by dt. I am going to write r I cap cross f I cap, because dl by dt nothing but torque. R I cap f I, sorry, R I bar f I bar. Okay, and see, this force is the combination of external forces acting on the particle and also the combination of internal forces, external forces and also internal forces. So we can write dl bar by dt, we can write R I f external plus R I f internal. Okay, previous derivation is enough, just I am giving the idea of the systems of particles. dl by dt, we can write external and internal, but these internal forces are zero. Why? Because from Newton's third law, each and every particle will create some action and reaction forces that will be cancelled. So internal forces nothing but action reaction forces. So these forces will cancel with each other. So internal forces will cancel with each other, only this will present. This is nothing but Ri bar cross F external. This Ri and F external, which is equivalent to torque. Again the same derivation. Okay, no need to worry about this. Okay, just I given some idea, so no need to worry about this. So in exam if they ask, better you can follow the previous derivation. Torque is equals to dl by dt, because I use L is equal to R cross P and I applied the derivative. Okay, so this I given an idea for systems of particles. For system of particles, they will give n number of particles whose masses they will give, and angular momentum just you add, you take the summation, apply the differentiation, again the same result. But this right side result is the combination of external forces and internal forces. Right side means all individual particles. That individual particle nothing but that is the combination of some external forces and internal forces. Internal forces will cancel with each other because of action and reaction pair. Only the right side will be Ri and F external. That Ri and F external, R cross F external will give torque. Again that torque which is equivalent to dl by dt. Okay, so leave this, just you follow the previous derivation. Please go through the NCERT, you will understand everything. I consider n particles and just I take the summation, I apply the derivative. This is equivalent to R and F, because this is a torque. Okay, total torque acting on the system of particles. Total torque nothing but R, F, and this F nothing but external forces and internal forces. Internal forces will cancel with each other, only external, that external nothing but tau external. Okay, so but you follow the previous derivation, that is easy. Why? Because what is the previous derivation? L is equals to R cross P, apply differentiation, directly we got tau is equals to dl by dt. Okay, now okay, so far we know relation between torque and angular momentum. Okay, now let me continue few basic problems based on torque and also angular momentum. Okay, so let us see whether it is coming or not. Yeah, write down one small problem. Okay, I'll continue problems based on torque with angular momentum, both at a stretch. Let me continue one simple question. A particle, so let me write, a particle of mass m is projected with speed v naught from P as shown. Okay, then they are asking find out torque at highest point and it is just about to hit the ground back. Yeah, this is the question. See, let me draw the diagram. I am continuing torque and angular momentum both at a stretch. So this is the particle whose mass is m. Yeah, this is the question. Read the question twice. Particle of mass m projected with a speed, how much they given? V naught. They are asking torque. We can find angular momentum also, that also I will continue. They are asking torque. Read the question. A particle of mass m projected with a velocity v naught from a point P, this is point P as shown. Find out torque at the highest point and also it is just about to hit the ground back. It is going to hit here. Now find the torque at two places. If they ask any other place, that also we can find. If they ask here at any point P or at any point something Q, at this point also we can find the torque. That also I will continue. Okay. So first let us try this. See, torque at the highest point. This is P something Q. This is something PQ. This is S. PQ S. At Q means highest point. Target is to find out torque. What is torque? Force into perpendicular distance. If the particle is at the highest point, then which side the force is acting? Force nothing but gravitational force. Gravitational force, that is mg. Mg acting downwards. Okay, mg acting downwards. force and perpendicular distance. Tell me, this force is acting downwards like this, mg. What is the perpendicular distance for this force about this point P? About the point P, tell me the perpendicular distance. mg, and this is the perpendicular distance. What is this perpendicular distance? Shall I write r by 2? What is our range? Range of the projectile, r by 2. Now the torque about point P, we can write it as mg into r by 2. What is this r? What is r? Range. Range formula, u square, u nothing but v naught square sin 2 theta by g. Already 2 is there. This 2 I am writing as it is, 2. So the answer is half. So g gets cancelled. M v naught square sin 2 theta is the torque about the point P. Got it? Torque about the point P is half mv square, nothing but can get half mv naught square sin 2 theta. And see, they are asking at this point, while it hit the ground, means if the particle is hit the ground, then the weight of the body acts vertically downwards and the perpendicular distance is r about P. Now at S, torque about P we can write it as mg into r. Got this point? Mg into r. Mg, what is the perpendicular distance? About point P. They are asking about point P. About point P is r. So mg into r. What is r? R nothing but v naught square sin 2 theta by g. Now the answer is m v naught square sin 2 theta. So that is the torque about a point P at the highest point, at this point. We can find at this point, everywhere we can find. By using some kinematic equation, we can find torque at any point. We can find angular momentum also. That also I am going to continue. Angular momentum and torque, both. Okay. So first write down this torque. So this is also an important concept, come problem. About highest point, at highest point calculated about P. At the last point we calculated about P. Now let me find at some other point. You take this one. Yeah. So the same question. Small change. Completed? At P as shown. So I am going to draw the diagram. This is the P. They are asking torque at this point. At the highest point calculated, at the last point also calculated, okay, before going to hit the ground also calculated. Now you try to find at a point P, at that point, means after some time interval, after a time interval of t. You try this, the same formula, torque is equals to force into some distance. Yeah. At point P, we don't know the particle is at what distance exactly. So resolve some distances here. See, this is at a distance of something x and this is at a height of y. So the point P, at P, the particle have some position vector. The position vector we can write it as x I cap plus what? Y j cap. Particle have some position vector. X I cap, y j cap. How to get this x I cap and y j cap? Tell me. X I cap. X nothing but horizontal component. I just recall kinematics. Okay. So this x component we can write it as C. This is the R. So R bar we can write it as x nothing but, I think you remembered, u cos theta I cap nothing but v naught cos theta I cap. Y nothing but like ut minus half gt square. Y component. Recall the projectile motion. X component, horizontal component is u cos theta. Vertically is y is equal to ut minus half gt square. Ut plus half at square. Plus half at square nothing but here a is minus because particle thrown into the air. So a is taken as minus. So ut minus half gt square. U nothing but v naught t minus. Okay. U nothing but vertical component v naught sin theta ut minus half g t square j cap. See, this is the R component. This I written from kinematics. Recall the kinematics. U cos theta I cap and y component means ut minus half at square. U nothing but vertical component. Vertical component is v naught sin theta into t minus half gt square and see, this is resolved into two components. Okay, this is v cos theta, horizontal component of remains constant, that never changed. Okay, if this is theta, what is this? V naught cos theta and this is vy. See, this is vx, vy, you know this thing. Okay. And see, I written here only t. X is equals to, this is vt, t. Okay. X is nothing but v cos theta into t. Just I written from projectile motion, horizontal component. X is equal to u cos theta into t. You remember, I think x is equals to u cos theta into t. Okay. And this is y component. Y is nothing but ut minus half gt square. So this is R. And let us write F. F nothing but, see, the weight of this particle is downwards. Weight of the particle downwards. Downwards means mg minus j cap. Mg minus j cap. Now, how to get the torque? Torque about P, we can write it as R bar cross F bar. Use the cross product again. Cross product, A cross B. So this value and this value. V naught cos theta into t I cap plus V naught sin theta t, multiply this one, j cap minus half gt square j cap cross mg minus j cap. See, almost I am doing kinematics here. R bar I written x I cap, x component, y component. X component nothing but x, horizontal component. Recall it. S is equal to ut plus half at square. Ut plus half at square. U nothing but u cos theta into t. U cos theta nothing but u replaced by v naught. V naught cos theta into t I cap. Y nothing but ut plus half at square. But a nothing but minus. So u nothing but uy, y component, v sin theta into t minus half gt square. Then only possible this one. Mg, weight is downwards. So do the cross product. If we do the cross product, v naught cos theta into t. Okay, here directly. So I cross minus j. I cross minus j. So let me multiply minus here, minus and j. Plus This entire value having j and j cross j 0. Then answer is minus v naught cos theta into t. What is I cross j? I think you know this one. I j, directly we can write k. What is I cross j? I cross j is k. So k cap. Now the answer is minus v naught cos theta into t k cap after a time t. Okay, so this is the torque at a point p after a time interval small t. Minus v naught cos theta into t k cap. And one more is missing. See, multiply. See, v naught cos theta into t, mg is missing. Mg I cross j minus written already here. T mg k. Check this answer. Recall this one from kinematics, motion in straight line. Okay. So horizontal component S is equal to ut plus half at square, a0, u nothing but u cos theta, u nothing but here v naught cos theta into t. Vertical component S is equal to ut minus half at square, u nothing but u sin theta into t, half at square, a nothing but minus g. Okay. And do the cross product, you will get the answer. Okay. Let us find angular momentum for this projectile motion. Find angular momentum of a projectile at maximum height as shown at maximum height. So direct formula this one. Particle of mass m moving with a speed something v naught. Yeah. Find angular momentum of projectile at the maximum height. At the maximum height. Find this one. See, earlier I calculated torque. Now I am going to find out angular momentum. Okay, there are plenty of models. Based on the situation, I am going to cover everything. Angular momentum at the highest point of a projectile, at the maximum height of a projectile. So, you know angular momentum, nothing but what? MVR means momentum into perpendicular distance. Momentum is mv nothing but mv naught. R nothing but perpendicular distance. This is R. This R which is equivalent to height. What is that height? Maximum height. So, MVR we can replace with mv naught h. This is the formula. Direct. mv naught h. So, mv naught, okay, v naught h nothing but, see if it is projected at the highest point, what is the horizontal component of velocity? V replaced by v naught cos theta, recall the projectile, and this is h. So v nothing but v naught cos theta, h is nothing but maximum height of projectile, u square sin square theta by 2g, u here v naught square sin square theta by 2g. Then answer is mv naught cube cos theta sin square theta by 2g. This is the angular momentum of a particle at the maximum height of a projectile. If theta is given something 45, if particle thrown by making something 45 degrees, then we can find angular momentum. M V naught square cos 45, 1 by root 2, this is 1 by 2 by 2g. Now 2 this is 4, M V naught square 4 root 2g. If it is given 60, whatever will be if the angle is mentioned, substitute angle, you will get angular momentum at the highest point of a projectile.